Jupiter, our largest planet, is a swirling world of storms, moons, and immense forces still being unraveled. At over 300 times Earth's mass, it acts like a miniature solar system. Jupiter has 95 known moons, including the Galilean moons, 4 massive satellites, one of which, Ganymede, surpasses Mercury in size. Since arriving in 2016, NASA's Juno spacecraft has delivered stunning images of Jupiter, Ganymede, and Europa while unlocking secrets about its atmosphere and powerful magnetosphere. Jupiter's magnetic field is the strongest of any planet in the solar system, more than 20,000 times stronger than Earth's. This massive magnetic field plays a crucial role in the planet's atmospheric dynamics, influencing not only the formation of dark ovals but also creating stunning auroras. Unlike Earth's visible auroras, Jupiter's can only be observed in ultraviolet light, making them invisible to the naked eye. Both phenomena are caused by the same magnetic interactions, indicating the immense energy passing through the gas giant's atmosphere. The influence of this magnetic field extends far beyond the poles. It shapes Jupiter's vast radiation belts, traps charged particles, and even dictates the movement of its volcanic moon Io. The interaction of these forces makes Jupiter a unique laboratory for studying the physics of magnetospheres and their impact on planetary atmospheres. The storms of this immense planet have fascinated scientists for centuries. For example, the Great Red Spot has been a constant feature of Jupiter's atmosphere for over 350 years. Recent images taken by NASA's Juno spacecraft show that the storm is shrinking over time, yet it remains large enough to engulf several Earths. Beyond the iconic Great Red Spot, Juno has discovered complex storm structures known as corrugated filamentary regions, typically found at subpolar latitudes. These areas feature thread-like clouds and are woven with broader turbulent patterns. It seems that these filaments represent regions where atmospheric layers are vigorously interacting, creating unique features unlike anything seen on Earth. Jupiter's atmosphere is inextricably linked to its magnetic field. Jupiter's atmosphere is a realm of extreme phenomena. Let's take a closer look at these Earth-sized storms born from magnetic tornadoes. These are phenomena as dissimilar from Earth's weather as the size of Jupiter itself. These storms manifest as dark ovals, first spotted in ultraviolet images from the Hubble Space Telescope in the late 1990s. For decades, their origin remained a mystery, but recent studies have revealed a fascinating link between the planet's powerful magnetic field and these extraordinary atmospheric events. Recent observations by Planetary scientists, led by Troy Sabata and his team, have uncovered the mechanism behind these phenomena. Each dark oval forms in Jupiter's polar regions, places where the planet's magnetic field lines converge and interact with charged particles. These particles, coming from Io's plasma torus, a donut-shaped ring of volcanic material ejected by the moon Io, race along the magnetic field lines. When the magnetic field of the plasma torus interacts with the field lines closer to the planet's atmosphere, friction creates magnetic vortices. These vortex structures, resembling tornadoes, descend deep into the planet's stratosphere, where they lift aerosols, creating a dense haze visible in ultraviolet light. These appear as dark ovals in the images. Planetary scientists describe Jupiter's poles as magnetic tornado alley. Storms appear with astonishing regularity at the southern pole roughly 3/4 of the time in annual Hubble imaging from 2015 to 2022, and more sporadically at the northern pole. Unlike Earth's tornadoes, which arise from temperature and pressure differences, Jupiter's counterparts owe their existence to electromagnetic forces. Each vortex forms a storm so large that Earth's entire diameter could fit inside it. The haze inside these dark ovals is extraordinarily dense, up to 50 times denser than the surrounding atmosphere. This density suggests that the aerosols are not only lifted from deeper layers of the planet, but are also actively concentrated through the vortex motion of the tornadoes. While the exact chemical composition remains unknown, the formation process provides a window into the turbulent interaction between Jupiter's upper and lower atmospheres. These discoveries offer invaluable insights into the mechanics of the gas giant's weather systems. The enormous scale of these storms, combined with the unique forces driving them, presents a striking contrast to the atmospheric phenomena we observe on Earth. Looking at Jupiter's turbulent atmosphere and generally at its immense size, one might assume its surface lies hidden beneath the clouds. However, Jupiter is fundamentally different from rocky planets like Earth. It has no solid ground. Instead, its structure transitions from gas to liquid and possibly to a dense, mysterious core at extraordinary depths. Understanding Jupiter's internal structure is key to unraveling the formation of gas giants and the dynamics of our solar system. Jupiter is composed mainly of hydrogen and helium, the same elements that dominate the Sun. Starting from its upper atmosphere, Jupiter's clouds consist of ammonia and water with traces of methane and other compounds. These clouds form the colorful bands and storms visible from space. But as we delve deeper, the atmosphere becomes denser, forming a thick, gaseous layer stretching thousands of kilometers below the surface. This composition hints at the planet's origins. Like the Sun, Jupiter formed from the primordial nebula that birthed the solar system. However, it lacked the mass to ignite nuclear fusion and become a star. Instead, it remains a failed star, preserving its primordial gases, which provide a glimpse into the conditions of the early solar system. Beneath its visible atmosphere, pressure and temperature rise sharply. At a depth of about 1,000 miles, hydrogen begins to behave more like a liquid than a gas. This transition doesn't happen straight away. Instead, it happens gradually, creating what scientists call the largest ocean in the solar system, not of water, but of liquid hydrogen. At this depth, immense pressure, millions of times greater than atmospheric pressure at sea level, compresses hydrogen molecules, forcing them into a liquid state. This liquid layer extends tens of thousands of kilometers, creating a vast and exotic environment unlike anything on Earth. The Moon's rocky mantle potentially creates hydrothermal vents similar to those found on Earth's ocean floors. These vents, driven by tidal heating from Jupiter's immense gravitational forces, could provide the energy and nutrients necessary to sustain life. Ganymede and Callisto, although less geologically active than Europa, also possess subsurface oceans. Ganymede, the largest moon in the solar system, has a thick ice shell and a layered ocean structure that may extend over 100 miles deep. Meanwhile, Callisto's ocean, though less explored, is believed to be relatively stable and offers a different environment for potential habitability. The presence of liquid water is a key ingredient for life, but it is not enough on its own. Salts and organic molecules detected on Europa's surface, likely originating from its subsurface ocean, provide further evidence that the Moon has the necessary raw materials for life. Data gathered by the Europa Clipper and JUICE missions will be crucial for future exploration. Instruments on these spacecraft will identify areas with thin ice or water vapor plumes venting into space, offering accessible targets for future probes or landers. These missions may include advanced drilling systems capable of penetrating the icy crust to sample the ocean directly or robotic submarines designed to explore the liquid environment. Exploring Jupiter's oceanic worlds marks the beginning of a new era in the search for extraterrestrial life. Europa, Ganymede, and Callisto are not just icy moons but dynamic worlds with hidden oceans that may harbor life. While the Europa Clipper and JUICE missions race toward their destination, we don't have to wait years to explore Europa thanks to NASA's Europa Trek platform. Anyone with an internet connection can take a virtual stroll across this alien moon today. This interactive site offers a detailed virtual tour of Europa, allowing users to explore its mysterious surface and learn about its geological features. The Europa Trek platform uses high-resolution images captured by the Voyager 2, Galileo, and Juno missions to create a comprehensive interactive map of the moon. Accessible at trek.nasa.gov/Europa, the platform allows users to zoom in on Europa's icy plains, examine ridges and cracks, and analyze craters in stunning detail. By clicking the hamburger icon, users can access the guided tour feature by selecting Landforms of Europa, which showcases some of the moon's most intriguing landmarks, providing both scientific context and captivating visuals. One of Europa Trek's standout features is the ability to measure distances and surface heights. This function is especially valuable for scientists and educators, offering a tool for remote study of the moon's geology. Europa's surface is crisscrossed by long, dark lines called lineae, believed to represent fractures in the moon's icy crust caused by tidal forces generated by Jupiter's immense gravity. For example, Belus Linea stretches for thousands of kilometers and is one of Europa's most prominent surface features. The platform also showcases areas with chaotic terrain, where ice blocks appear to have broken apart and refrozen in new configurations. These regions may indicate past or ongoing activity beneath the ice, possibly linked to a subsurface ocean. Another noteworthy aspect is the scarcity of impact craters on Europa, indicating a young, geologically active surface. One prominent crater, Tyre, is a multi-ring structure spanning 87 miles, providing insights into the Moon's surface age and its response to impacts. As the Europa Clipper and JUICE missions approach their targets, their high-resolution data will likely enhance the platform, adding new layers of information and improving our understanding of Europa's surface and interior. In the meantime, virtual exploration of Europa serves as a reminder of how technology can bring the mysteries of the universe closer to us. Whether through a computer screen or instruments aboard a spacecraft, the quest for answers has already propelled humanity into a realm once thought unreachable, a world of discovery. The solar system is unique. In 20 to 30% of similar planetary constellations, the central star absorbs the planets that revolve around it. But if that's the case, why didn't this happen to us? The answer to this question may lie in the largest and oldest planet of the solar system, Jupiter. It is possible that before Earth, Venus, and Mercury, there were other planets. However, they may have been destroyed by Jupiter, laying the foundation for the current solar system. In fact, what if Jupiter originated outside of our star system? Today, we'll talk about the hypothetical migration of the gas giant and how this may have affected life on Earth. Jupiter is a huge planet composed entirely of gas, mostly helium and hydrogen. The first studies of Jupiter took place back in the 17th century, but many aspects remain unsolved to this day. For example, Jupiter's most notable feature, the Great Red Spot, GRS, is still controversial in scientific circles regarding its origin, length of existence, and color. Jupiter's rapid rotation around its axis, approximately 9 Earth hours, creates lengthy and powerful cyclones and anticyclones that can reach speeds of 335 miles per hour. The Great Red Spot is an anticyclone that has existed for over 300 years. However, the GRS is decreasing in size. In the 19th century, the size of the anticyclone was estimated to be 25,500 miles wide, but now it is slightly larger than Earth's diameter at 10,250 miles. The reason for the GRS's size decrease is still unclear, but NASA scientists suggest that unknown atmospheric activity may weaken the wind currents. Another mystery of the GRS is its signature red hue. Scientists suggest the cause of the redness may be ammonium hydrosulfide, a colorless gas that forms sulfur when exposed to solar UV radiation. Furthermore, NASA scientist Amy Simon believes there is a correlation between the intensity of the storm's color and its speed. According to her research, the color of the GRS becomes more saturated when the wind speeds increase. In addition to helium and hydrogen, Jupiter's atmosphere contains heavy elements such as nitrogen, argon, and xenon. These elements could only form at very low temperatures, possibly far from the Sun, leading scientists to theorize that Jupiter may not have originated in its current position. This gas giant could have formed 4 times farther away from the Sun and later migrated closer, completing its formation. For brevity, I'll stop here. According to astronomer Phil Plait, in addition to water, meteorites containing building blocks for living organisms, such as amino acids, from which proteins are formed, were also brought to Earth. Therefore, Jupiter may have been one of the reasons for the origin of life on Earth. In a way, Jupiter can even be considered our shield to some extent. The gravity of the gas giant can change the trajectory of dangerous asteroids and comets, steering them away from Earth. Furthermore, Jupiter is capable of absorbing comets that have the potential to become a threat to other planets. For example, in 1994, the 1.2-mile-wide comet Shoemaker-Levy 9 crashed into Jupiter. If this had reached Earth, all life on our planet would have been doomed. However, in order for water to exist on Earth as abundantly as it does now, Jupiter most likely sent asteroids in our direction. That is, Jupiter does not always protect us. On the contrary, it can also be a source of attack. Professor John Horner of the University of Southern Queensland has determined that Jupiter increases the risk of asteroids colliding with our planet. Nevertheless, If Jupiter had a smaller mass, it would have dramatically increased the possibility of cosmic bodies reaching Earth. Therefore, Jupiter definitely plays an important part in our life, but it also has the potential to harm it. Interestingly, there's another subtle influence that Jupiter has on Earth. The Earth's orbit is almost perfectly circular. However, due to Jupiter's gravitational pull, it can stretch into an elliptical shape. This deformation of the orbit leads to significant climate changes. Summers become much hotter and winters much colder. Of course, this does not happen very often, only every 45,000 years, but we are currently in the midst of that cycle. The migration of Jupiter has not yet been confirmed and requires further research. However, it is likely that without the gas giant, our solar system would be completely different. It is possible that without its influence, life on Earth may not have existed at all. In 2021, NASA sent the Lucy spacecraft to explore the Trojan asteroids. Perhaps its expedition will reveal more data to confirm the hypothesis of Jupiter's migration and may also allow us to study the material from which our universe was formed more than 4 billion years ago.